Welcome back, everyone, to this series of lectures discussing the mathematical theory as well as the motivation and intuition behind logistic regression. In part 1, we'll begin by discussing the logistic function itself. Logistic regression in general works by transforming a linear regression into a classification model through the use of the logistic function shown here. Let's begin by understanding the history and motivation behind the logistic function, otherwise known as the sigmoid function. And the sigmoid function or logistic function simply takes in a value of x and then outputs 1 over 1 plus e to the negative x. And we'll soon learn that this has many advantages for us as we begin to discuss the machine learning classification model that is going to transform linear regression to a classification model using logistic regression. To be clear though, you should note that right now we're just referring to the logistic function itself, not the full logistic regression model. So this history that we're about to discuss is just referring to this logistic function, this formula shown here. Beginning in the 1830s all the way to 1850, through a series of publications under the guidance of Adolphe Quetelet, Pierre-François Verhulst developed the logistic function. As a quick note, we've seen that earlier machine learning models have independent developments, and it's no different for logistic function itself. In 1883, the logistic function was independently developed in the field of chemistry as a model for autocatalysis by Wilhelm Ostwald. But let's first focus on the first developments of the logistic function all the way back in the 1830s. The main purpose for its development was to actually model population growth. And in fact, we can see here the original publication comparing the otherwise known logarithmic curve versus the logistic function curve. You can see that the logarithmic curve is the one on top that is slowly growing exponentially, and the logistic curve tends to level off. So the question arises, why do we have this need for modeling purposes of the logistic function versus the previously known logarithmic function? If you actually plot out the sigmoid or logistic function, you can see the behavior shown here, where we get this curve and eventually a leveling off. And in fact, you should note that there is a family of logistic functions, many of them based on the hyperbolic tangent. And as I mentioned, you should notice this leveling off behavior of the curve. And you should notice it going in both directions for x negative values and x positive values, where we have this curve limit to 0 as you go negative, and this curve limit to 1 as you go positive. So there's, again, those two characteristics, the leveling off features in both directions, and the notification that any value of x will have an output range between 0 and 1. And the important thing to realize here is that many natural real-world systems have what is known as a carrying capacity, or some sort of natural limiting factor. And this could be everything from world population growth, where if you look up projected world populations, it seems to follow this trend of a logistic function, where there is some sort of exponential curve that's growing, but eventually you get this leveling off as the growth rate declines because of limiting factors such as carrying capacity. And it just isn't with model populations, but also for many different scientific fields. Here we can see the sugarcane yield in Australia versus the depth of water available. And again, you get this sort of limiting factor where just natural real-world systems have some sort of limit where you get this leveling off effect similar to a logistic function. So clearly a logistic function itself can be really useful for modeling these systems that have this carrying capacity or natural limiting set of factors. Then, moving on into the 1940s, the logistic function was used for statistical modeling, and this is where we actually begin to develop logistic regression. So moving beyond just the logistic function itself, Joseph Berkson actually began to develop the statistical model that we know as logistic regression today, while it was able to take in more than just a single feature. And in 1944, he published the application of the logistic function to bioassay in the Journal of the American Statistical Association, which is generally referred to as kind of the first major publication showing the application of logistic function for the purposes of a statistical model, eventually known as logistic regression. An interesting quirky fact about Berkson is that while he may have been an absolute expert coming to the statistical modeling field, he was actually a prominent opponent of the idea that cigarette smoking causes cancer. In fact, he was once quoted in Life magazine as being very doubtful that smoking causes cancer of the lung. So while we now know that smoking is clearly bad for you, we still haven't actually learned how to convert a linear regression to a logistic regression. So let's not take everything Berkson says as true, but we'll go ahead and take his developments of logistic regression as something we can rely on. Let's go ahead and continue on seeing how a linear regression is unable to solve classification problems effectively, and how the logistic function itself can help fix this by transforming linear regression to logistic regression. I'll see you at the next lecture.